Hey everyone, welcome to our Lightweight Structures final project. My name is Mo,
I'm Ephraim.
Caleb.
And I'm Kevin.
and this is our MECK chair design.
For our design project, we wanted to design a chair based on the IKEA pillow chair. We chose this design because it would be more simple to analyze using FEA and analytical methods. However, it would be complex enough to warrant significant analysis to understand. Through extensive analysis of the chair and its components, we hope to meet all four failure criteria to ensure that the occupant of the chair is safe and secure.
Here we have the blueprint of our chair. So we designed our chair to be made up of two arm and leg combination pieces and the seat and back to be made out of one piece. So this W here is the width of the chair, arm and leg, and T is the thickness of the plate. And so these two are the variables that we want to optimize. The back of the seat is oriented 30 degrees counterclockwise from the vertical, and the seat is 5 degrees counterclockwise from the horizontal to create a comfortable seating position. All of the measurements shown here are in centimeters. So again, here we have our chair components. So for the arm, we wanted to make it out of oak wood, specifically northern red oak. We chose it for its characteristics of strength and longevity. Oak wood is also heavyweight and has a tight grain pattern, making it unlikely to split down the grain pattern. For our seat, we decided to make it out of 304 stainless steel, and we chose it for its resistance to corrosion and modern aesthetic. So we want our chair to be able to support 115 kilograms, which is around the industry standard. Based on a government study that we found, it was determined that body weight is distributed about 78% on the seat, 13% on the back, and 18% on the floor. These forces will cause reaction forces in the connections at point A and C, which we established as pins. These reactions are also the forces that will act on the arms. So here we have the forces that are acting on the plate. We split the plate into two sections, the back and the seat, and we have reoriented them to make them easier to analyze. Here we have all the forces that act on the arm and leg combination. So we split each arm into 5 different sections, 2 horizontal beams, 1 vertical beam, and 2 bent beams.
Here are all the values of the forces and general stress equations. F1 and F2 are the given forces based on the max weight capacity with our safety factor of 1.25 already being applied to the forces. When solving for the reaction forces, we made several initial assumptions to simplify our results. The first of these would be that each body is rigid so that we could avoid the forces changing as parts would bend and move. The second would be that each joint between parts would be treated like a pin or hinge joint. The last of these would be that the reaction forces are based on our maximum theoretical loading based on our applied forces. We found that the chair itself is statically indeterminate based on our first two assumptions, so we considered the reactions would go far beyond what we realistically expect in compensation. In doing so, we decided we could avoid the analysis on the curved sections as our amplified forces would cover any higher concentrations of stress we might normally have. These are the equations of our bending, normal, and shear stresses. In these calculations, we lifted the rigid body assumption and calculated our standard normal and shear stresses, as well as our flexural stresses, which are denoted as sigma max and tau max. Here, the variable q represents the first moment of area of our beams, and I is our moment of inertia. These are our final stresses we found in each beam. Because each stress was solved in relation to the width, we would only need to solve for the minimum width based on our axial stress applied at beam 1 and the buckling at beam 3. Here we have the seat on the left and the back plate of the chair on the right. Below the seat, we have our corresponding force and stress calculations, and to the left of the back plate, we have its calculations.
Okay, so moving on to the failure criteria. Heading into our initial analysis, we were mainly focused on the effects of yielding and buckling on the chair, because the flexure and stiffness that it would experience would be much smaller in comparison. Yielding was one of our primary concerns, simply because of the high load our chair would experience. Since we wanted our design to support a weight of up to 115 kilograms, which is 253.5 pounds, all our failure calculations were done with this weight in mind. As for buckling, the slender wooden legs of the design would experience a compressive force because of the body weight pressing down on them. That being said, we still wanted to ensure that the flexural and stiffness failure criterion were met, just to guarantee that anyone using the chair wouldn't experience any injuries. So combining our structural analysis with our failure criteria, we can calculate the minimum mass for both the wooden and metal components of the chair. In our equations for area and volume at the bottom of the slide, W represents the thickness of the wooden arms and T represents the thickness of the metal bodies. So after doing all of the required analysis, we found the minimum width of the wooden beams to be 2.63 centimeters under yielding and 0.04 centimeters under buckling. As for the plates, the minimum thickness was calculated to be 0.00128 centimeters, which was under yielding. The value for buckling was a very small decimal value, and therefore buckling was found to be insignificant for both the seat and the back. Moving on to minimum mass. For the plate, we found a minimum mass of 6.3 kilograms. For the arms, it was 3.69 kilograms, for a total of 10.5 kilograms.
To corroborate our results from our handwritten solutions and analysis, we use finite element analysis through the SOLIDWORKS simulations add-on. By replicating the normal force and reaction forces that we obtained by the structural analysis, we were able to receive the results shown on the left and right figures. On the left, you can see that the legs experience a low amount of stress, and even at the pinholes, which are stress concentrators, the stresses do not approach the yield strength. On the right, it is apparent that most of the deformation on the wooden legs occur at the elbow closest to the ground, which makes sense considering the compression that the chair experiences. We also conducted a finite element analysis on the steel base of the chair. In contrast to the handwritten solutions, I modeled force 1 and force 2 as a distributed load rather than point forces. However, we are still able to gain valuable insights from this analysis. While the back of the chair experiences low stress, the seat area experiences a lot of stress, concentrating on its outer corners. It would be in our best interest to fillet the sharp edges of our seat. However, no parts of the chair experiences yield strength. As expected, most of the deformation of the steel base occurs near the outer edge of the seat area, having a downward displacement of upwards to 5.5 millimeters at the edge. This is definitely an area in which we need to focus on properly supporting to ensure the safety of the chair's occupant. Through our extensive analysis of our lightweight structure, the MECK chair, we are able to conclude that the buckling criterion is not a concern as a mode of engineering failure. However, we must consider the high concentration of stress that occurs in the metal seat area to ensure that it does not experience yield strength. In addition, the elbow of the wooden leg closest to the ground experiences a considerable amount of deformation, so we must better support the wooden leg to guarantee the comfort of the chair's occupant. Lastly, while our design meets 2 out of the 4 failure criteria with flying colors, it is worth noting that while steel is a tough and reliable material to handle high loads, that it is very dense and can add a considerable amount of weight to a lightweight structure. We will work hard to ensure that our design also meets the flexural and stiffness failure criteria as well. I would like to thank you for taking the time to listen to our presentation on our MECK chair design. We hope that you gain insight regarding the design and analysis of a lightweight structure. Take care and stay safe.